Hello everyone. Can someone confirm if am I audible?
Yes, sir, you are audible.
Thanks. Is my presentation visible?
Yes, sir.
Yes, sir.
Okay. Let's wait for 2 more minutes for others to join. Then we will start today's session. Okay, I think we can start today's session. So, good evening, everyone. My name is Arpit Bal, and I am a PhD scholar at IIT Bombay. So, I am also the recipient of PMRF fellowship, and so I have taught previously in NPTEL Digital Circuits course in the previous semester. So for this semester, I am your NPTEL PMRF TA. For the Digital IC Design course, which is being taken by Jan.2024 sir, and I am in the Integrated Circuits and Systems specialization at IIT Bombay. I completed my BTech from IIT Bhubaneswar in 2020, and after that, I was working briefly with TCS Research. After that, I joined as a PhD scholar here. Okay, so without further ado, let's start today's session. So let me tell you about the motivation of these sessions. So whatever lecture material has been covered through the NPTEL coursework, so these sessions will help you to improve your problem solving skills. So in these sessions, we will be solving a few numericals related to whatever was covered in each week. So for this course, so for this particular live session 1, we will be covering some problems related to week 1, and that will help you in solving the assignments that is given to you for the week 1 course. Secondly, so what I will suggest is grab a pen and paper, and I'll go through the questions and I'll suggest you to try out the answers with me and verify whether like you are able to solve those questions or not. If you are facing any issues, let me know. Okay, so I hope this is clear. So is everyone with me?
Yes, sir.
Okay.
Yes, sir.
Yeah. Okay. So in week 1 lecture, so these were the topics that were covered: PN junction diode, MOS capacitor, MOS transistor current equation, body effect, and short channel transistors, and velocity saturation as well. Okay. So these are some important equations that we will be using in today's tutorial. So I will suggest you guys to note them down. And so the first one is for the V threshold, the VTH equation, along with the body effect. Okay. The next one is the IDS, or the drain current equation. Okay. So these two equations we will be using in today's tutorial. So please note them down. So let me know if I am going fast so that I can slow down. Okay. Okay, and note this down as well. So given any transistor with certain parameters, so we need to figure out what is the region of operation that transistor is in, and based on that we need to find out what is the drain current, right? So there we will need the help of these equations, and also this V min. So as we saw in the so here this V min term is present, right? So we need to replace that term with the V min given here for NMOS this one, and for PMOS this one. Okay, so let me admit the other students.
Sir, some problem in a channel length modulation in a saturation region. In a previous slide, there is a this is I saw this is a linear region, I think.
So this equation can be used for everything. Okay, so that's why this is a unified formula, and while solving the questions I'll make it clear how we can use it for different regions.
Okay, sir.
Okay, so this same equation is going to be used, but it is dependent on this V min. Okay. Okay, and note down this thing as well. So you need not note this one, but okay. So I think this was the question that you were asking, right, Devendra?
Yes, sir.
Yeah. So basically you can see that in linear, this is the equation being used; in saturation, this one, and in velocity saturation, the third equation. But basically all the three equations actually can be written in this format. Okay, and in each of the cases we are actually replacing the V min, and if we replace the V min term in each of the cases, then we can arrive at this equation. So you can try this one out. Okay. The next thing is, so as I mentioned that we can figure out what is the region of operation of transistors from the V min itself. So if the V min that is obtained, so let us take the case of NMOS transistor. Okay. So if the V min obtained is VGS minus VT. So what I will do is, let's say you are given a transistor in which you know the VDS, the VDS SAT, the VGS and the VTH, right? So first thing you do is find out what is the VGS minus VT. Okay. Next thing, you know the VDS and you also know the VD SAT. So if you notice that the minimum of all the three values, it turns out to be VGS minus VT, then the transistor is going to be in saturation. Okay. So these things have already been covered in the lectures. I'm just brushing it up so that we can get ready for today's problem solving session. Similarly, so if Vmin is equal to VDS, so if the minimum out of these three terms is VDS, then the transistor is going to be in linear region. Okay. Similarly, if the V minimum turns out to be VD SAT, then the transistor is going to be in velocity saturation region. Okay. So with this, we can start the problem solving session for today. And this is the common data that we will be using. Okay. So please note down these values as well.
Hello. So one doubt I have in the
Yeah,
previous slide.
Yeah.
Yeah, sir. In the first, if V minimum is VGS minus VT, that means VDS and VDS set are greater than VGS minus VT.
Correct.
But sir, if it is like that, VDS set is more greater than VDS, then the transistor will be in saturation or not? Means, sir, VDS set is the minimum VDS required for saturation. If VDS is greater than VGS minus VT, but VDS is less than VDS set, then transistor will remain in saturation or not?
Sorry, can you repeat your question?
Sir, suppose VGS minus VT is 1 volt.
Okay.
VDS is 2 volts and VDS sat is 3 volts.
Okay.
Then will it be in saturation or not?
Yes,
Means minimum VDS required is more than the VDS present.
Okay. Yes. Yeah, it will be in saturation.
Okay, sir.
Okay. Yeah. So let us start the problem solving session.
Sir, I have a doubt, sir.
Venkat.
Is it, see, the condition what you have explained earlier for NMOS, is it valid for PMOS also?
Yes. So in today's session, actually what I planned is like we will have roughly 4 or 5 questions related to NMOS and there will be one PMOS question as well. And I think that PMOS question will clear your doubts related to that question which you asked. So instead of V minimum, what we are going to do is for PMOS we will be using
V max.
Correct. Okay. So just like we told that if it is VGS minus VTH, if that is the minimum for NMOS.
That is maximum. In case of PMOS, we will consider maximum.
Correct. So just like in case of NMOS we took minimum, if this one is the minimum, then it is going to be just a minute, let me add the student. Yeah, okay. If this is the minimum, then it is going to be in saturation. If VD sat N is the minimum, then it is going to be in velocity saturation. And if VDS is the minimum, it is going to be linear region. So this is for NMOS. Similarly, if VGS minus VTH is maximum, then it is going to be in saturation for PMOS. If VDS is maximum, it is going to be linear. If VD sat PMOS is maximum, then it is going to be in velocity saturation.
Okay, sir, it is clear.
Okay. So actually it will be more clear when we are solving the problem. So you can draw a parallel analogy, like this is the way how it is solved for NMOS, and so that PMOS question that we will come, I think question number 4, that will help you to understand it better. Okay, let's start the session. So we have, so consider an NMOS transistor of W by L is equal to 5 lambda by 2 lambda, and we need to calculate the drain current ID in microamps for VGS is equal to 0.89 volt and VDS is equal to 0.6 volt. Okay, assume that VSB is equal to 0. Okay, so the first thing that we need to do is, let us figure out what is the VTH. Okay, so using the working equation for VTH, we have VTH is equal to VTH naught plus gamma root over of mod VSB plus psi s minus root mod psi s. Okay, but it is given to us that VSB is equal to 0. It means this will be mod psi s minus mod psi s. So this complete term will be 0 and we are left with VTH naught. Okay, and VTH naught for NMOS is given to us as 0.35 volt. Okay, so this data is already given in common data. So I'll wait for a minute so that you can note down this common data, because we are going to use this data in the complete problem solving session. Okay, so I'll wait for only 1 minute, so please note it down as soon as possible. Once you have noted it down, please you can type in the chat box that done. Okay, is it done? Should I wait or can we proceed? Okay. Okay. Yeah. So let's proceed. Okay. So as we know that VSB is 0, so our V threshold is going to be VTH naught, that is 0.35 volt, and it is mentioned in the common data that we saw in the previous slide. Okay, so once we know the VTH naught, we know the VTH, let's figure out what is VGS minus VTH. Okay, because after figuring out the VTH, the important thing that we need to do is we need to figure out what is the region of operation of transistor. Okay, and to figure out the region of operation, we need all these three values. Okay, this one, VDS and VDSAT. Okay, VDSAT is already given to us, VDS is already given to us. We need to figure out VGS minus VT. Okay, so VGS is given to us as 0.89 volt minus VTH is 0.35 volt. Okay, so this is equal to 0.54 volt. Okay, this is first thing. Secondly, it is given to us that VDS is equal to 0.6 volt. Third, VDSAT is equal to 0.5 volt. Okay, so out of these three values, the minimum is 0.5 volt for VDSAT, which means this region of operation is velocity saturation. Okay, so we are going to use the VD sat value in the Vmin equation. Okay, so we will have ID is equal to mu n Cox W by L VD sat VGS minus VTH minus VD sat by 2 into 1 plus lambda VDS. Okay. Okay, so you might be having a question that why did I do 1 plus lambda VDS? How do I know whether to operate in short channel or long channel, right? So okay, did I mention 2 lambda? Okay, yeah. So it is mentioned here that it is 2 lambda, right? So if it is mentioned in the question that what is the value of L, okay, then from there you can estimate that whether you have to go for a short channel equation model or a long channel model. Okay, let us assume that W by L would have been given to you as 50 lambda by 20 lambda. Okay, then you can observe clearly that the L that we are using is roughly 20 times the feature size. Okay, the minimum length. Okay, so it means then we can go for a long channel assumption easily there, and we need not consider the 1 plus lambda VDS for that case. But in this case, because it is 2 lambda, so we need to consider the short channel effect. Okay, so using this equation, okay, and another thing, yeah, another thing, so mu n Cox, so mu n Cox is represented as Kn dash. Okay, so what we will do is we have Kn dash W by L VD sat n VGS minus VTH minus VD sat n by 2 into 1 plus lambda VDS, right? Let us call this as ID, and let us call this complete equation as ID dash. Let's find out ID first. Okay, so ID is Kn dash is given to us as 210 into 10 power minus 6. W by L, is there any specific value up to which we can consider length as short channel? Yeah, sure. So I think the safe assumption will be if you have a very huge number associated with the length, like as you mentioned 10 lambda, so I think that's a safe assumption to say that it's a long channel. Okay, and less than 10 lambda you can go for the short channel assumption. Okay, yeah, so 210 into 10 power minus 6 into the aspect ratio is given to us as 5 by 2. Okay, into the VD sat n was 0.5 into VGS minus VTH that we found out to be 0.54 minus VD sat n by 2, okay, is equal to 210 into 10 power minus 6 into 2.5 into 0.5 into 0.29 is equal to 76.125 microamps. Okay, so roughly we can say it is 76 microamps. Okay, this is ID. So ID sat is 76.125 microamps into 1 plus lambda VDS. So lambda VDS is 0.07 into VDS that is given to us is 0.6. Okay, so this will be 79.32225 microamps, that is roughly 79 microamps. Okay, is this part clear? Is this question clear, or does anyone have any doubt in this question? Okay, I'll just take 1 minute, wait for 1 minute for everyone to note this down. So the recordings will also be available to you on it will be, the link will be shared by the NPTEL team with you guys, but if anyone has any doubt and they want to ask now, they can ask. Okay, else we can move to the next question. Okay, so this is unused page. Okay, so yeah, please go ahead, Gaurav.
Sir, please give the criteria to consider the channel length modulation or not, sir. Whether it is short channel or long channel. So
Okay.
what should be the ratio of W by L?
No, ratio of W by L won't decide your channel length modulation or not. The L itself will decide the channel length modulation. So if you see, okay, in this question, we see that L is 2 lambda. Okay, so
Yes.
if you see an L that is within 10 lambda range, okay, it is safe to go for short channel effect. So assume channel length modulation.
So whatever be the W, W not
Yeah.
affect.
Yeah, W won't affect. The L affects the channel length modulation. So you remember that image that was like during the lecture. So sir drew an image, right? That the drain and source are separated, and in short channel device it comes closer. And because it comes closer, the diffusion region that is formed between the body and the N plus region, right? It becomes deeper and deeper. Okay, so basically there the shit, man. Hello. Yeah, sorry, I lost internet connection. Am I audible now?
Yes, sir.
Yes, sir.
Now,
Just give
yes,
me
Yes,
1
sir.
minute. I'll reshare the screen. Is my screen visible?
no, sir.
Okay, is it visible now?
Yes, sir. Mm.
Okay. Yeah, so I was answering someone's question. What is the difference between 5/2 ratio and 500/200 ratio? Okay, so there is no difference when aspect ratio is considered, but 500/200 ratio, you can safely assume that it's a long channel device, and you don't need to consider the channel length modulation in that case. Is that clear, Akash? Okay. Okay. So previous question we did it from a very practical point of view, but now I want you to repeat the same question, considering the transistor to be a long channel device. Yeah, Devendra.
Sir, my doubt previous Akash told that 5/2 ratio,
Yeah.
and 5/2 ratio is a sort L equal to 2 lambda,
Correct.
in which is we can apply short channel
Yes.
this condition,
Yes.
or 500/200 this is a long channel, I
Correct.
think. Okay, sir.
So if you assume that 5/2 is also a long channel device, let us say, because in this particular question we are going to do that assumption. Okay, so then because the aspect ratio is same, the currents will be equal. Right, if you consider the 5/2 to be a long channel device, so in terms of current there won't be any change if you consider it to be a long channel device. But from practical point of view, if you are having an L which is very short, then you need to consider the short channel effects like channel length modulation. Is that part clear?
Yes, sir.
Okay. Okay, so we have to repeat question 1, considering the transistor to be a long channel device. Okay, so if we are considering the transistor to be a long channel device, okay, we have only two variables now, VGS and VDS. Okay, so we are not concerned about the VDSAT for the time being. Okay, and we know that out of these two, VGS minus VTH, and we know the VGS minus VTH is 0.54 and VDS was given to us as 0.6. Okay, so the minimum of these two variables, it is 0.54. Right, so it means the transistor is in saturation, and we can directly use the saturation formula without using the 1 plus lambda VDS thing as well. Okay, so ID is equal to half Kn dash W by L VGS minus VT whole square, okay, equals half. So Kn dash is 210 into 10 power minus 6. W by L is 5/2. Why we are ignoring VDSAT here? Because in the question it is mentioned that it's a long channel device. Okay, so the concept of this VDSAT, it comes into picture when we are considering a short channel device, right? Because okay, in the lecture it was also explained that so we have E is equal to VDS by L, right? If it is a short channel device, then the L is going to reduce. Okay, but because the L is going to reduce, then there is a chance that there can be breakdown, right? So because of this, with decreasing the L, we also need to reduce the supply voltage. Correct? But then what we get to know is even if the supply voltage is dropped, so there is a particular maximum value of drift velocity that can be attained, that is 10 power 5 meter per second, right? And VDSAT is defined based on that. VDSAT is equal to when your drift velocity is obtained into L by mu n, that is the mobility factor, right? So this thing comes into picture only in short channel device. So because of that reason, we are not considering any VDSAT here. Does that answer your question? Okay. Yeah. So did anyone try to calculate this? This is roughly 76.545 microamps, right? $75.54. Is there a typo? Can see. Calculate. Yeah, 76.54. Yeah, okay. Okay, so moving on to the next question. Okay, so in the previous questions, we did not consider the presence of body effect, but as we know, presence of body effect is going to affect our VTH. Okay, so in the previous question, VSB was 0, so VTH was equal to VTH naught. But in this question, it is assumed that VSB is equal to minus 0.1 volt. So now let us see how the calculation changes. Okay, so the first thing that we are going to do is calculate the VTH, that is VTH naught plus gamma square root of mod psi s plus VSB minus square root of mod psi s. Okay, VTH naught is already given to us as 0.35 volt plus gamma is 0.4 plus 0.3 minus 0.1. Okay, VSB is given to us as minus 0.1. So for the students who joined late, so the value for VTH naught and gamma, it is as well as psi s, it was already mentioned in the first slide, okay, where we had the data to solve all the tutorial questions for today. Okay, minus mod psi s is 0.3, sorry, square root. So we will have 0.35 plus 0.4. This is square root of 0.2 minus square root of 0.3. That equals 0.35 plus 0.4. And this is roughly 0.4 into 0. Just a minute. Square root of 0.2 minus square root of 0.3. It is minus 0.1, around minus 0.1. Okay, that is approximately equal to 0.31 volt. Okay, so this is our VTH in this case. Okay, so now like we did in the previous case, rest everything will be same, but only the VTH is going to change. We have figured out what is the VTH. So can anyone tell me what should be my next step?
Finding V minimum.
Correct. So for finding V minimum, we need to figure out what is the minimum of VGS minus VTH, VDS and VDSAT. Okay, VDS is given to us, it is 0.49. Can someone compute VGS minus VTH?
0.58.
0.58. Yeah, that's correct. So VGS is given to us as 0.89 minus VTH is given to us as 0.31. So that is 0.58. And out of these, which one is the minimum and what is the region of operation?
Linear.
Correct. Because VDS is minimum, so our region of operation is linear, and we will use the Vmin value as equal to VDS. Okay. So let me write down the ID formula. Mu NCox W by L VGS minus VTH into VDS minus VDS square by 2. And okay, let me see whether I need to put the channel length modulation. Okay, nothing specifically mentioned, and it is given as W by L is equal to 5 lambda by 2 lambda. So we have a channel length modulation here. Okay, and this is our Kn dash. So we have Kn dash into 5 by 2 into, this is 0.58 into 0.49 minus 0.49 square by 2 into 1 plus lambda is 0.07 into 0.49. Okay, 210 into yeah, so someone raised their hand. Devendra, you have a question?
Yes, sir.
Yeah, sure.
Sir, in this we are use linear region. Can it possible the 1 plus the mostly short length CM short length modulation in saturation region only? Can it possible in linear region also?
Sorry, I didn't get the question.
We use the linear in this. We find this MOSFET work on linear region, and we are applying short channel length modulation.
Yeah, that's a good question. Okay, mostly it operates in saturation when the short channel effect is taken into consideration, but if it is linear, why can't we use the 1 plus lambda VDS? Yeah, I think it can be used, right?
Okay.
210 into 10 power minus 6 into 5 by 2. This is 0.164. Okay. Yeah, Venkat, you have a question?
Sir?
Yeah, you have a question. You raised your hand.
I have one doubt, sir, regarding ID and IDS.
ID and IDS. Okay.
See, in case of NMOS, when we calculate IDS in this case, so IDS will be the positive number.
Yeah.
But the value of ID as per this description, ID refers to current into the drain. Then shall we put negative
For
sign
PMOS.
for that?
Yeah. Yeah, it's a sign convention. So you can put, yeah, means if you are putting positive for NMOS, like put negative for PMOS. Okay.
No. See, IDS is current from drain to source as per the notation, right?
Okay. Yeah. Yeah, but
But
we write it as ID usually.
But in the assignment, it is given that ID refers to current into the drain.
Current into the drain. Okay.
In that case, what I am feeling is we should write ID is equal to minus of whatever the value we get for IDS. Is it okay, sir?
Yeah.
Here I have the doubt.
Yeah. Actually, I think that is means you are moving in the right direction, but I can't give out this answer because this is a part of your assignment question, right? So you're
part of the assignment, but see, if we are not clear about the description, we cannot give the correct answer. See, everything may be correct, but just because of that sign, we may miss the mark, and it may happen in many questions.
Yeah. So if you are considering from ID to S, you can put a negative sign. But usually what I have seen is ID is considered, means the ID in NMOS is considered as positive.
Okay.
And in PMOS it is considered to be in negative.
Okay, thanks.
Okay, so after 3 questions in NMOS, let's try out 1 question in PMOS. Okay, so we are given a PMOS transistor with W by L is equal to 5 lambda by 2 lambda. Okay, we need to calculate the VTH, the drain current ID, for given VGS is equal to minus 0.5, VDS is equal to minus 0.6, with assumption that VSB is equal to 0.1. Okay, so I'll show one thing. So here in the common data, you see that Kp dash is given to us as 110 micro. Is this screen visible?
Yes, sir.
Okay.
Yes, sir.
Kp dash is given to us as 110 micro amps per volt square, but there is a modulus sign before that. Okay, so this is exactly for the direction of current thing that was asked by Venkat. So that's why whenever we are writing the equation for ID for PMOS, we are going to use minus 110 microamp per volt square, whereas other parameters like let's say it is operating in saturation, so I will have an equation half mu n Cox W by L VGS minus VTH whole square, right? So the component that is present inside the VGS minus VTH whole square, that cannot be negative because it is being squared. Next thing, W by L cannot be negative, right? Because it's an aspect ratio. And we know that Kp dash is going to be negative. So that's why we can safely assume that ID for PMOS is negative. So does this answer your question, Venkat?
Yes, sir.
Okay, great. So and ensure that you are following the same sign convention everywhere so that you don't get confused. So because we took PMOS as negative, so NMOS we have to keep everything as positive. Okay, so now let us start solving this question. So we have VTH is equal to VTH naught plus gamma square root of mod psi s plus VSB mod minus root of mod psi s. Okay, and VTH not mod of VTH not P was given to us as 0.35 volt, right? So we will write it as minus 0.35 volt plus gamma was given to us as mod gamma P was given to us as 0.4. So we will write it as minus 0.4 square root of modulus psi s was given to us as minus 0.3. Sorry, mod psi s was given to us as 0.3. So psi s is minus 0.3 plus VSB is given to us as 0.1 volt. Okay, minus square root of mod psi s, that is 0.3. Okay, minus 0.35 minus 0.4 square root of 0.2 minus 0.3 is equal to minus 0.35 minus 0.4 into minus 0.1. Okay, so this will be minus 0.35 plus 0.04 is equal to minus 0.31 volt. Is this calculation clear for everyone, or is there any confusion in the signs that have been used? Is everyone clear about this? Because writing the equation wise everything is fine, but when people write the equation for PMOS, people get confused in the sign conventions that are being used. So what I will suggest is stick to the same equation. The only thing that you need to change is whatever VTH or any value that is given in modulus, so take the negative value in the entire equation. Okay, and then you can arrive at the correct solution for PMOS. Okay, I'll take a 1 minute pause here for everyone to look at this, and then we will proceed with figuring out the region of operation for PMOS. Okay, let us move to figuring out the region of operation. Okay, so now VGS minus VTH is equal to, so let's see what was the VGS given to us. VGS was minus 0.5 minus VTH was obtained to be, VTH was obtained to be minus 0.31. Okay, so VGS minus VTH is minus 0.5 plus 0.31. Okay, that is minus 0.19 volt. Okay, then VDS was given us to be minus 0.6 volt. Okay, and VDSAT, so mod VDSAT P was given to us as 0.5, so VDSAT is minus 0.5 volt. Okay, let us revisit the Vmin that was mentioned. Okay, so for the case of PMOS, the Vmin was maximum of these three values. Okay, so we have three values, minus 0.5, minus 0.6, minus 0.19. So can anyone tell me what is the region of operation?
Saturation.
Correct. Because VGS minus VTH is the max, so this transistor is in saturation. Okay, let me write it properly. Okay, So I hope identifying the region part is also clear in this case. So someone in the beginning, he asked me about the PMOS thing. So is this clear how we identified the region of operation for PMOS? If it is clear, please let me know through the chat box. If anyone has a doubt, just let me know. Is it clear? Okay, then, okay, great. So then we can move to finding out the current. Okay, half mu PC aux W by L VGS minus VTH whole square 1 plus lambda VDS. Okay, this is our KP. So half into KP into W by L VGS minus VTH whole square into 1 plus lambda VDS is equal to, KP has a negative value, that is minus 110 by 2 into W by L is given to us as 5 lambda by 2 lambda, that is 2.5. okay, and VGS minus VTH, so VGS minus VTH was 0.19 that we figured out okay here. So this is into 0.19 square, so there is a minus sign, but it is square, so that's why I just ignored the minus sign here. 1 plus, so lambda for this case it was given to us as 0.11 minus 0.11 into the VDS. The VDS was minus 0.6. okay, is equal to, so can someone try to solve this? Okay, I missed 10 power minus 6 to 10 power minus 6 into 1.066, okay, equals minus 5.29 microamps. Okay, is this question clear?
Yes, sir.
Okay, does anyone have any doubt in this question? Sorry Gaurav, can you be a bit louder? I can't hear you. Hello? Am I audible?
Yes, sir, you are audible.
Okay.
Yes, sir.
Okay. Gaurav, can you be a bit... okay. Yeah, Devanand. Okay. Gaurav, you can type your message on the chat box. Actually, your voice is a bit feeble, so I can't hear you. Okay, meanwhile, we will try to solve the next question. Okay, so in the next question, it is given to us that consider an NMOS transistor of W by L is equal to 60 lambda by 20 lambda. Calculate the drain current ID, sorry, I missed the D, in microamperes for VGS is equal to 0.92 volt and VDS is equal to 0.5 volt. Assume VSB is equal to 0 and round your answer to nearest integer. So in this question, can someone tell me whether I need to consider the short channel effect or not?
No, sir.
No, sir.
Okay, great. So how did you determine that?
And
length is
Yeah,
larger.
correct. So because this L that we see, it is 20 lambda, so we can directly go for a like we can ignore the short channel effect. Okay, so we will first figure out what is the region of operation of this transistor. That is, we will do VGS minus VTH. Okay, and VSB is given to us as 0 volt. So just like in the first question we saw, if VSB is equal to 0, then there is no body effect involved, and because there is no body effect involved, the threshold voltage is not going to be changed and it will be equal to VTH naught. Okay, so it means I can write VGS minus VTH naught itself. It is 0.92 volt minus 0.35 volt, that is equal to 0.57 volt, and VDS is equal to 0.5 volt. Okay, so because the minimum is VDS, so what should be the region of operation of this transistor?
Saturation.
Linear.
Correct. It should
Saturation.
be no, it should be linear, right?
Linear.
Yes, linear.
Yeah. Okay, so we have ID equals mu n Cox W by L VGS minus VTH into VDS minus VDS square by 2. Okay, because this is our Vmin, I just substituted the Vmin present here in the original unified equation that we saw. Okay, and this is our Kn dash. So I'll write 210 into W by L in this case is 3, and VGS minus VTH is 0.57 into VDS is 0.5 minus 0.5 square by 2. Okay, so please calculate and let me know what is the final answer.
Sir,
Yeah,
I might doubt that in this place we not applied V minimum concept.
why not? Because V minimum is VDS, so we substituted V minimum here, right?
So V minimum 0.5 na.
Is that clear, Devendra?
Yes, sir. Yes, sir.
Okay. Yeah, so let me know what is the final answer. Yeah, correct. So 100.8 is the correct answer.
100.8.
Yeah. Okay. So let's move on to the next question. Okay, so in this case it is given to us that the NMOS transistor in question number 5 in the previous question has W by L equals to 6 lambda by 2 lambda, VDS is equal to 0.55 volt, and VSB is equal to 0.1 volt. Calculate the drain current ID in microamps, round your answer to nearest integer. Okay, so now can someone tell me whether we need to consider the short channel effects or not?
Yes.
Yes, sir.
Correct.
Yes, sir.
So this is because the length is 2 lambda. Okay. And because the length is 2 lambda, so we have to consider the short channel effects that is going to occur. Second thing, do we need to consider the body effect here?
Yes, sir.
Yes.
Okay. VSB is equal to 0.1 volt. Right. So because of body effect, our threshold voltage is going to change. So let us find out the threshold voltage first. Plus gamma square root of mod psi s plus VSB minus square root of mod psi s. Okay. 0.35 plus 0.4 square root of mod 0.3 plus 0.1, so sorry, this is modulus, minus square root of 0.3 equals, so can someone calculate this? 0.4, this is 0.632 minus 0.5477.
Point 3838.
0.3838. Okay, so approximately I'll write it as 0.3839 because the next significant is actually 38389 something, right? Okay, so this is my VTH. Oh wait, I'll add a page. Okay, so we have the VTH value here. What we need to figure out is what is VGS minus VTH. Okay, so VGS, we are going to use it from the previous question. We took 0.92 minus VTH is 0.3839, that is equals 0. Okay, so can someone tell me what is the region?
Velocity saturation.
Saturation.
Correct, because VD sat is the Vmin here, so we are going to use velocity saturation. Okay, now let's figure out what is the drain current. Okay, this is our Kn dash W by L VD sat N VGS minus VTH minus VD sat. What will be the nearest integer for 0.38? Wait, what is this question? What should be the nearest integer for 0.3838? Which answer box? Sorry Sumit, I didn't get your question. The assignment question. Oh, I don't know. Like, you figure out which one is more suitable. So this is just an rounding of small assignment. So we are not supposed to give any solve any assignment questions here. So you figure out whichever you think is suitable. Okay. 1 plus lambda VDS is equal to 210 into W by L is 6 by 2 into VD sat N is 0.5. VGS minus VTH, it is 0.5361 minus 0.5 by 2. Okay, and 1 plus lambda is 0.07 and this is 0.55. Okay, can someone solve this question? Sorry Gaurav, that particular question I won't be giving the answer, so you figure it out on your own. Yes, you will get the PPT. So I think the NPTEL team must have shared a sheet which mentions the place where my this particular recording will be visible, as well as the slides will be visible. 93.59, yeah, that's the correct answer. 93.59 microamps. Okay. Yeah, so this PPT as well as the recording will be visible. So the recordings is will also be available after 8:30 today. So it will be available in my so we have a YouTube channel for all the live sessions that are being conducted. For me it is please share the YouTube link. Okay, just give me a moment. Yeah, so I'll upload it here, and this complete lecture PPT that we covered today, so even this will be available to you. So NPTEL team will share the link. Yeah, so these were the questions that I thought we will solve today, and so let me revisit all the questions so that we have a let me summarize this. Okay, and what I will suggest is please so in each of the tutorial sessions, so it is expected that both I will solve the question as well as you will solve the question. So this will improve your problem solving, your practice. Okay, and it will, like, the more problems you solve, the better your concepts will be cleared. Okay, so today's session we started with the important equations that are needed. Okay, the next thing, how to determine the region of operation from V min. Okay, we basically take the minimum of these three things, VGS minus VT, VDS and VD sat, if it is given that the device that we are using is an NMOS. If the device what we are using is a PMOS, we need to figure out the maximum of these three. Okay, and the region of operation will be the same, like instead of minimum of these three, if we find out maximum of these three and it turns out to be VGS minus VT. Okay, so for PMOS that will be in saturation. Okay, so now you can figure out the analogy for the rest of the cases, right? VDS linear for NMOS, and similarly for PMOS, VDS will be linear if VDS is max, right? Okay, in the first question it was given to us that VSB is equal to 0 volt, and we saw if VSB is equal to 0 volt, it means this second term, which is involved in the body effect part, it goes to 0. Okay, it means there won't be any change in the V threshold, the threshold voltage, right? So VTH is equal to VTH naught if it is given to you that VSB is equal to 0 volt. Okay, next thing that we need to do is we need to figure out what is the region of operation. To figure out the region of operation, find out what is VGS minus VTH, see where does this particular thing stand when compared with VGS minus VTH, VDS and VDS SAT. Okay, VDS SAT will be provided to you in the question itself. So in this case, we used the common data that was given to us. Okay, and you figure out which is the minimum of these three, provided your device is NMOS. Had it been PMOS, you need to consider the maximum. So please be careful while solving the numericals in this way. Okay, and so the concepts that we are clearing, it will not only be helpful for solving your assignments, it can be helpful for your future exams that you are going to write. Okay, so here we saw that the VGS minus VTH was 0.54, the VDS was 0.6 and VD SAT was 0.5. So we saw the VD SAT obtained the minimum value. So we can safely say that the region of operation is velocity saturation. Okay, there is a question. Is there any possibility that current will get saturated in linear region? Why will it get saturated in linear region? Sorry, I actually didn't understand. Dhananjay Rao, can you explain what do you mean by current will get saturated in linear region? Do you mean it will stay constant? Like in short channel. Like in short channel, you considered VD SAT. Okay. No, it won't, right? Means, see, I think while solving, you may arrive at such a condition, but most likely it is because you are not taking the other significant figures. Okay, but yeah, but this thing that it will get it is not going to get saturated if it is in a linear region. Okay, then there is one more question for PMOS, where to take positive sign and where to take negative sign. Okay, yeah. Okay, so this question, Gaurav, will come back to that question just after one more question that is present here. Okay, so here what we did is, like, we figured out what is the minimum, and based on that we substituted that in terms of instead of Vmin. Okay, so because VD SAT n was minimum, we replaced VD SAT n here. Okay, so in question 2, what we were supposed to do is we were supposed to repeat the previous example, considering it to be a long channel device. Okay, so because it's a long channel device, yeah, because we were asked to consider it as a long channel device, that's why we did not consider the channel length modulation parameter. Okay, the next question, we need to consider the body effect here because VSB is non-zero. Okay, so the first thing that we figure out is what is the VTH. Okay, so based on the working equation that we mentioned earlier, VTH is VTH naught plus gamma times square root of mod psi s plus VSB minus root over of mod psi s. Okay, you figure out what is the VTH. Once we figure out the VTH, we go around with the same way. We figure out what is VGS minus VTH. We figure out whether which one of the following is minimum, and based on the Vmin we figure out what is the region of operation. Okay, for this case the region of operation was linear because VDS was minimum. Then we substitute VDS instead of the Vmin in that unified equation and solve the question. Okay, now coming to the PMOS part, I think Gaurav, this is where you have a doubt, right? So where do we need to take positive sign and where negative sign? So for PMOS, the VTH0, okay, let me go back to the data that was provided. So in the common data, you can see all the values for PMOS. It is given within a modulus, right? Similarly, let's say it is Kp dash, that is mu P Cox. Okay, same thing for VD sat P, gamma P, psi SP. Okay, so wherever this mod and mod VTH not P. So wherever you see a mod for the PMOS, you need to consider all those things as negative. Okay, now let us go back to our question. Okay, so VTH0P, it was given to us that mod VTH0P is equal to 0.35. So I just took the negative sign. Okay, similarly it was given to me that mod gamma P was 0.4. So again I took a negative sign. Okay, same thing, mod psi S was given to me as 0.3. So I just took psi SP is equal to minus 0.3. Right? And then I solved. Okay. So is that question clear regarding where to take positive and negative for PMOS?
Yes, sir, now clear.
Okay. Yeah. Okay. So this is how we figured out what is the VTH that we need to use for our equation. Next thing what we do is we figure out VGS minus VTH, VDS and VDSAT. Okay, and like how we did it for NMOS, it was we figured out what is the minimum of these three, but for PMOS we need to figure out what is the maximum of these three. So the maximum of these three is minus 0.19. That is VGS minus VTH, and because it is VGS minus VTH that has the maximum value, so the transistor is operating in saturation region, and we will use the equation for saturation region. Okay, so here again, so mod Kp was given to us as minus 110. Sorry, mod Kp was given to us as 110. So here we will take a minus sign. Okay, same thing with lambda P.
Yes.
Mod lambda P was given to us as 0.11. So lambda P is minus 0.11. Okay, so this question should clear your doubts regarding whether to take minimum, how to find out the region of operation, what sign to take when PMOS is considered, because mostly we deal with NMOS, so people have some sort of confusion with PMOS related questions, but I think this particular question will solve that confusion. Okay. And next thing was related to, I mean, it's similar question, but here we were assigned L is equal to 20 lambda. So the motivation behind this particular question was to understand where we can ignore the short channel effect, right? So here we see L is 20 lambda, which is 20 times greater than the minimum length. So we can simply ignore the short channel effect and go on solving our question. Okay. In the next question, we saw another example where 2 lambda is given. And as we mentioned that if we have it in the range of less than 10 lambda, then we should go for short channel effect. Else we need to, we can simply ignore the short channel effect, right? So here we go on considering the short channel effect as well as the body effect because VSB is non-zero. Okay. Then we proceed to figuring out what is the region of operation. and next we figure out what is the ID. Okay, so that's all. So this was the end of today's live session. So I'll still be around for 15 to 20 more minutes. So if anyone has any doubt in the questions that we solved or the lessons that were covered in week 1's course, so please feel free to ask me. Yeah, and this complete live session is available on that NPTEL channel, and it is also the entire slide will be made available to you by the NPTEL team. So I think by 8:30 that this particular recorded lecture will be uploaded, and you can revisit that. And it is better not only revisiting but trying out the problems parallelly. So you can take a pause where you find that it is a bit fast. So I just need one feedback. Is the content like whatever we were doing today, was it fast or was it medium paced? Was it fine?
It's comfortable, sir.
Okay, thanks. Did anyone find that the pace is a bit fast and I need to slow down?
Was good.
Okay. Medium. Okay. Yeah. Thanks. So yeah, just let me know if you face any problem, and if anyone has any doubt in week 1's course content apart from what we have covered today, so they can ask me.
Sir, can you explain the velocity saturation part one more time?
Yeah, sure. So velocity saturation. Okay, so okay, so you know that E is equal to VDS by L, right, where E is the electric field. Okay, so earlier when we were considering long channels, okay, let's say earlier the channel length in consideration was 180 nanometer. Okay, so it means the E is going to have a value, let's say X.
Okay.
But with scaling of technology, this L, okay, this is actually L. So this is going down and down. Let's say now it is 22 nanometers. Okay, is it updating late?
Yes, sir.
Okay. Is it updated?
Yes, it is.
Okay. So now we have scaled it down to, let us assume that it is 22 nanometer. Okay. So when we go on decreasing this distance between source and drain, the problem is this E rises now. Now it will be some X plus, such that X plus is greater than X.
Yes.
But the problem is, if we go on increasing the electric field, there is a possibility that there is not a possibility, it will actually lead to breakdown. Okay, so with reducing the technology node, we also need to reduce the supply voltage.
So is this electric field from gate to drain, gate to body side, from gate to body side?
From source to drain.
Okay.
And okay, so because of this reason, now what we need to do is we need to scale the VDD with technology. Okay, but in spite of dropping the VDD, there is only a maximum drift velocity that the electron can obtain. okay, in this lattice, okay, and that is like 10 power 5 meter per second, okay, and we know that this, okay, this is the velocity, this is the mobility, and this is the saturation velocity, okay, and this left hand side, I know that there is a maximum value to it, okay, it can't go beyond 10 power 5 meter per second,
Okay.
okay, so there will be a particular voltage at which that velocity is obtained, and if I apply a drain voltage which exceeds this VD sat further, okay, there won't be any further increase in current.
So when it exceeds the saturation velocity, then it will increase. VD will increase.
Sorry,
it will be saturated.
Yeah, it will be saturated. So there will be no further increase in current. Okay. So this is the issue with like scaling technology node where the short channel effect become more prominent. Okay. Yeah. So is there any other question that needs to be addressed? Please solve the some junction capacitance problems before 7th Feb. Deadline of second assignment. Okay. Second assignment. Okay. So our next session. So every Tuesday from 6 p.m. to 8 p.m. we have this session that will be taken by me. And there is another session that is, I think, running from Monday to Monday. Okay, so next session we have on 6th February. Okay, same timing, 6 p.m. to 8 p.m. So there we can solve some problems related to junction capacitance. Is that fine, Rahul? Okay. Yeah, so someone has raised their hand. Okay, that hand is gone. Yeah, Devendra.
Sir, my doubt that we found out the linear saturation, and also we compare the voltage with the velocity, but both are the different unit.
No,
How to possible
we don't compare the voltage with velocity.
For the minimum find in NMOS, we found the minimum voltage, VGS minus VT, VDS, and V velocity.
Correct.
So my doubt that voltage and velocity are different unit. Compare in possible in same in unit, no?
Where did we?
Yeah. Yes, sir. Yes. The previous slide just. One previous slide. Yes. That point. Yes.
Okay.
Yes, sir. Next. Yes, sir. That point. VGS minus VT. This voltage. VDS also voltage. VD saturation. I think is a value you also told. This is the velocity.
This is voltage. Okay, wait. You are confused with VD sat N and that small VDN. So, okay. VD sat N is the voltage, that is not velocity. So, velocity saturation is a different term. So, this is actually small Vn. Velocity.
Okay, sir.
Okay, so I didn't derive it, like it can be derived from this thing, right? Vd is equal to mu into E. where E is the electric field and nu is the mobility. Okay, and I just replaced whatever E was present here in this equation. Okay, and I told that there's a maximum velocity with which electron can travel even if I scale the supply voltage, and we scaled the supply voltage so that to prevent breakdown.
Okay, sir.
Okay. Yeah, is there any other doubt or any other question that you need clarity for? Let me check the chat box. YouTube link, yeah, I think I shared. Okay, I'll reshare it again. Yeah, this one. So it will be uploaded after I think by 8:30 it will be uploaded. Is there any difference between depletion charge and inversion charge? Okay. So I think they refer to the same thing which contributes in the channel formation. Okay. Is there any other question? It will be more convenient if these classes are on Saturdays, because some days scholars couldn't get time in the weekdays. Okay. Actually, I can't shift it to Saturdays or Sundays. So my allotted day is Tuesday 6 to 8. But okay, if this is a problem, so what you can do is, okay, no, Saturday will not be feasible at my end. Yeah, but if this is a problem, then what you can do is you can go through the recorded lectures that recorded sessions that will be available on that channel, which the link which I shared, and during the complete duration, whenever within 6 p.m. to 8 p.m, whenever you have a doubt, so you can just jump in and you can ask your doubt, whatever you have. I mean, that's the only thing that I can do. Will that be fine, Akash and Devendra? Because Saturday, any other day won't be feasible. Okay. And sir will share the notes. Yeah, these slides will be shared with you, but the NPTEL team will share with you guys a link. Okay, so I have a drive folder in which I upload these slides, so you will have access to the complete drive. So each week, whatever I explain, whatever we cover, so that will be uploaded. And yeah, one more thing, so I'll suggest you to go through each week's lecture contents first, so that it will help you while solving the tutorial sessions. So I mean, it's better to have a background in that one. So yeah, and yeah, so if anyone has any other doubt, let me know. Should the unit of gamma be v to the power 0.5? Okay, let's see. So we will just do dimensional analysis here. So this unit is v. Okay, this unit is v. So we need to add same unit. So this complete unit should be v. Okay, so here we know there is a VSB, so it means this unit will be v, this unit will be v. Okay, this complete unit is square root of v. Okay, so what should be the unit of gamma such that the complete unit of this term is v? Square root of v into x is equal to v, right? So x is again square root of v. So that is same as v to the power 0.5. Is that clear, Aditya? v to the power minus 0.5. Okay, no, it should be v to the power 0.5. Yeah. Is there any other question? Okay, then we will meet next week, same time, 6 p.m. to 8 p.m. So I hope these tutorial sessions are useful, and yeah, we can then wrap up the session if you guys don't have any doubt. Okay, I'll still be here. If anyone has any doubt, just let me know. Yeah, Sagar.
Okay, thank you.
Yeah, okay, yeah, sure. Yeah, does anyone have any doubt in the questions that we have solved, or uh, in week one's whatever lecture was covered?
Sir, this video is recorded or not?
Yeah, this video is recorded, and it will be available to you after 8:30 today. And I have shared the link to the channel as well, so you can go through that. Even the slides, whatever questions we solved, right? These slides will be made available to you by the NPTEL team. So, yeah.
Okay, sir. Thank you, sir.
Okay, no problem.
Sir, hello.
Yeah.
Sir, is there any spice model means we have to we have to simulate that model? So any software freely available on
Yeah,
net or
you can
on
try NGSpice.
NGSpice, sir?
Yes.
Okay, sir. Thank you, sir.
Yeah. Do you need the link for NGSpice? You can try it out. So NGSpice is open source. So yeah, this is the link. Okay.
Okay. Thank you, sir.
Yeah. Okay. Okay, then we will wind up today's session. Thanks everyone for joining.
Thank you, sir.